very pleased that we have you today at our TUKE Space Forum webinar, which is sixth in this spring. And let me introduce our speaker. So Benjamin Joachimi is a reader of astrophysics at the University College London, and he obtained his PhD at the University Bonn in Germany 10 years ago. And after postdoctoral research at the Royal Observatory in Edinburgh, in Scotland, he joined the academic staff in the Department of Physics and Astronomy at UCL in 2013. And Benjamin is cosmologist with focus on exploiting large galaxy surveys. The research in his group ranges from processing state-of-art survey data to modeling astrophysics and cosmological signals to applying modern concepts of statistics and machine learning. Benjamin has been working on the ESA Euclid mission for over a decade now, and for his work he was awarded an Ernst Rutherford Fellowship and Royal Astronomical Society Fellowship and Ras Winton Award. Now I will stop sharing my screen. Please, Joachim, share your screen, and we are very interested to your presentation.
Okay, yeah. Hello, everyone. It's a pleasure to talk to you virtually. I'll try to share my screen and see if that works. See what happens now. That hasn't quite worked yet. I guess you see a black.
Now we see it. Now it's okay.
That's better now. Okay, brilliant. Okay, I think are we ready to go ahead?
Yes, please.
Excellent. Okay, right. So I am going to talk to you about Euclid, as Pavel already explained kindly. It's a forthcoming ESA mission, and it's going to explore the dark side of the universe. Now, what do we mean by this? And for instance, and in particular, how can we actually observe the dark side? So I'm going to talk to you about the science behind this mission, and then the probes that we use to actually uncover these dark ingredients of the universe, and then talk a bit more about the specifics of Euclid as it's now coming together at this time. Right, okay, so here we go, that's working. Now, if you take a look at this slide, we have what we call the cosmic pie, or the cosmic pizza, if you want. It shows you the composition of the mass energy contribution of the universe today. And the striking aspect is that all the colorful slices, that makes about 5% of the total matter, is stuff that we know. So all other areas of science essentially just deal with that amount. It's mostly hydrogen and helium left over from the Big Bang, the early universe, and you've got some extra bits in stars, as well as then heavier elements that were produced in supernovae and in the inside of stars. And that includes everything that you know and love and work with every day. Now, in the universe, however, a quarter roughly is made up of what we call dark matter. And although dark means it doesn't emit light directly to us, usually astronomers tend to call everything dark that they don't understand very well. So there's a bit of an inflationary use of the term dark. So dark matter, we know, holds objects together. We know that galaxies that are rotating would not work that way if we just count the normal matter. Galaxy clusters would not hold together if there wasn't an extra gravitating component. And even the universe itself would not have been able to build the structure that we observe today if there wasn't an extra gravitating component. And that is what we call dark matter. What it is exactly, we have frankly no idea at this point. Even worse in that regard is dark energy, shown here to be about 70% up to 75% of the constitution of matter and energy today. This was all invented and came about with the observation of accelerated expansion in the late-time universe. And that was done with supernova type 1a, and it received a Nobel Award not that long ago. So this dark energy is a very mysterious component. It permeates space, and it seems to drive the universe apart. So that creates the accelerated expansion, and through that also affects the geometry of the universe. For instance, by making look-back distances look even bigger than without this component. The more sort of sane ways of explaining this would be a cosmological constant as originally invented by Einstein. Vacuum energy has been proposed, but all of these have major issues, and everything else that has been proposed is far more exotic, and none of it is very compelling at this point. So any more information that we can gather on these two dark ingredients will bring fundamental physics forward enormously. Now the question is, they're dark, they're not emitting photons, and photons are still by and large the main source of information for astronomers. Now we have gravitational waves now, we're detecting cosmic rays, but by and large it is photons. So how can we get information on these components if they don't emit light to us? And the way forward here is actually an effect of general relativity that goes back to the very basics and fundamentals. And I'll try to explain to you briefly with one of Einstein's famous thought experiments that guided him in the early days of how this comes about. So you see that on this slide here. I wonder if you can see my pointer. I think you can, if I see that correctly. So I'll use that as well. We have here an experiment. We've got a closed box. We put an experimenter in together with a little ball here. And we have got two scenarios on the left and on the right. Once we put this box out into space, free floating, we put it into a rocket. That rocket is accelerating upwards. And then the experimenter will let go of the ball and observe what happens to it. And we can say what that is. The experimenter will observe that the ball accelerates towards the bottom, towards the floor of the box. As outsiders, of course, we see that the ball doesn't do anything at all. It's rather the floor of the rocket that's accelerating upwards, but it is in the end the same observation. Now, if we put that same box, same ball, same experimenter into a homogeneous gravitational field, let's say approximately at the surface of the Earth, it's standing still, nothing's moving, and the experimenter lets go of the ball, we observe something very similar. The ball is going to accelerate towards the bottom here. In this case, it's what we would call gravitational attraction. Now, there is actually something very fundamentally different between these two scenarios. Here, it is inertial mass that governs this. So inertial mass is essentially something that tells us how an object responds to a force by accelerating. It's the proportionality constant between that. It's Newton's second law. On the right-hand side, nothing is moving, but it's the law of gravity. So it's gravitating mass that dictates what the acceleration here is. Now, it is a bit of a coincidence or even a sort of miracle that in classic physics, these two scenarios yield exactly the same result as long as the acceleration is the same. We have done experiments and we find that inert mass equals gravitating mass to very high precision, but it is not explained in traditional sort of classical Newtonian physics. And physicists, of course, do not like these coincidences. And so Einstein solved this very elegantly by saying, well, I make this a principle. And he called this the equivalence principle. He said that these two scenarios here, left the rocket, right in the gravitational field, are essentially by definition indistinguishable. The experimenter will not be able to tell these two cases apart. Okay. And based on this equivalence principle, he then developed his theory of general relativity. He set out to explain motion in accelerated reference frames, so the left-hand side. Via this equivalence, he then quickly found, oh dear, I need to develop a whole theory of gravity to explain this. And then he went on to say, well, actually, this gravitation is not a classic force, it's actually free movement in a curved space-time, and that's where the complicated differential geometry comes in, and that's why GR is not very accessible and mathematically quite involved, but let's not go into that. This principle tells us a lot. Now, if we go to this case, slightly different experiment, but same situation. So now the experimenter has a torch, and she is shining a light perpendicular to the direction of acceleration. And imagine that this light ray now being a stream of photons that travel with a certain speed. And as long as the rocket accelerates and moves fast enough, what you see will happen is that the photons that were sent out earlier start to lag behind, because back here, the rocket was just over there, right? It's moving on this way. And so from an outside view, it looks like the light ray becomes bent in this direction. Now, by invoking the equivalence principle, we cannot say, well, we expect exactly the same thing to happen on the right-hand side. Nothing is moving though, but we should still observe a light ray that is bent towards where the gravitating mass sits. Okay, and that is indeed exactly what happens, and we call this the gravitational deflection of light, or as we shall see in a moment, it's also known as gravitational lensing. So this is one of the fundamental principles or observables that general relativity predicts, and you can understand it just from appealing to this basic equivalence principle. And actually, this gravitational lensing effect was the first experimental proof that GR was indeed the correct theory of gravity. And famously, this was conducted by Arthur Eddington. You see him here on the left, 1919, straight after the end of the First World War. And this is from a magazine article shortly afterwards. He set out, organized 2 expeditions, one to the west coast of Africa and one to Brazil, to observe a solar eclipse. And what they wanted to see is that, in this case, using the sun as the deflecting mass, that the stars behind get slightly displaced as shown here, and measure this effect. Now, there would be lots of fun stories to tell about this. This was an experiment beset with lots of problems involving strikes of steamboat captains and melting telescope equipment. No time to go into that detail. But long story short, the measurement was extremely dodgy, but Eddington was very determined and very convinced that Einstein was right, and he published this, and it made a bit of a furore. And this is actually the reason why, or the main reason why Einstein is nowadays a household name. Everyone knows him. It is gravitational lensing that made him famous in the end, due to this experimental proof. Again, as I said, it was very dodgy. It was repeated again later on. This is a measurement from the early 1920s. Still not really convincing quality of data. You see here, these lines are the movements of the apparent stellar positions, and the sum would be here in the center. If you average over all of this, you indeed find a displacement angle, and it was very nicely in agreement with Einstein's prediction. And if you do a very naive argument with classic gravity, which really is dodgy because light would never be deflected, it doesn't have a rest mass. But in any case, the Einstein prediction would be twice larger than anything you would predict traditionally. And indeed, the angle that was observed was much closer to what Einstein predicted. So that really nailed it. GR, general relativity, is the theory to go. Now, how can we use this to see the dark universe? By using this as gravitational lenses. So instead of the sun, we now look out further into the universe, where we've got much more massive objects. They act as the deflectors. And just like in lensing experiments that you've done at school, it's the same setup. You've got a source, a light source, you've got your deflector, your lens, and the lens will focus light rays towards you, the observer, either a camera or a telescope, to then see what happens. And to see what happens, there's a nice tabletop experiment that you can do. In this case, it's a ball lens. But if you don't have that at home, use the foot of a wine glass. They're usually curved in a way that represents astronomical sources quite well in terms of their mass profile. So just use the bottom of a wine glass, hold it against a candle, and you can see very similar effects. What you see there is that objects behind are displaced in angle behind it, they're pushed outwards, they're distorted into these sort of banana-shaped arcs, all tangentially around the center of the lens. You can see multiple images, so these might actually correspond to the same dot behind it. I'll illustrate in a second how that can happen. And they also look bigger, which means they're magnified. They work like a magnifying glass. All these effects can and are used in the universe to essentially find out about the properties of the lenses, so the mass that is behind it. And that mass can be light, can be dark, it doesn't matter. Everything that's gravitating is counted by this effect, and that's what makes it a very strong way to measure, for instance, dark matter. Okay, now let's look at a little example provided by ESA. The same kind of sketch here. We've got a background galaxy that emits light, and now we make a heavy lens And you see that the light rays are bent towards Earth. At some point we can observe them. In this case, 2 light rays are actually convergent onto our telescope. That means there are 2 ways that the same object can send us light. And indeed, you would then observe 2 images of the same background galaxy in a large, or behind a large cluster. And you see here also these arcs already, these stretched lights. These are background objects that have been distorted into these banana shapes, just as we saw with the tabletop experiment. The same version, again, static, just for you to see, but it's the same picture there. So this illustrates how we can even have multiple images. This happens if you get really lucky and if you've got a massive lens along the line of sight, so a big galaxy cluster. And that leads to these rather beautiful effects. Just to give you a sense of scale. Oh, I wasn't aware of this. It makes beautiful music as well. I'll try to make that a bit quieter. So you see as we zoom in, you increasingly see further and fainter objects appearing. So these are different galaxy surveys that are put together in this illustration. The key thing to note is the magnification is moderate. You can achieve that with a telescope that you have at home with you. The key thing is you need to collect light because these objects are faint. And so you need big telescopes to actually reach that point. And also you need to have good image quality to actually see these very small objects and resolve them. If you do that, you start to see these beautiful effects of gravitational lensing here in this example cluster. As I said, these are very special places in the universe. However, absolutely beautiful ones. Here, wonderful example, it's an Ebeling cluster, so one of the largest bound structures in the universe. And you can stare at this image for a while in your own time. You can actually, even if you just step back, you see these tangential patterns around the center of Mars. So even if I somehow blocked out the light of this massive object, you could guess actually where the Mars would sit. And that is exactly what we can do. We can measure these distortions, the positions of multiple images, and we can use that to weigh the cluster in the foreground that does the lensing. And in this case, you find something like 10 to the 15 solar masses. So these are really massive objects. And we can even look at how the mass is distributed as a function of radius. So we can learn how mass is assembled there. And indeed, we do find there's much more mass than the light emitted, just counting the starlight that we see here, would suggest. And it's actually more by a factor of 5 or so. So again, that hints at the existence of dark matter. Now, again, these are very special places. So if we want to find out about dark matter in the universe as a whole, that will not help us very much. But there's something else you can do. So again, this picture here shows the outskirts of a massive Ebeling cluster. You see here these distortions, so that's all fine. We could do our what we call strong lensing analysis with these beautiful images here. But once we go further out here, let's say this bit, you see lots of very faint, low resolution specks here, not very spectacular. These are very faint background images. They are affected by this large mass over density here. You just can't see it because galaxies tend to be elliptical just by themselves. For instance, imagine you're looking at a spiral galaxy edge on, it will look like so cigar shaped, right? It has a strong ellipticity in it. And that will be slightly, ever so slightly changed. So there's no way of telling this from a single object. Here, bottom left, you see what I'm talking about. This is vastly exaggerated. What we typically have in the universe is that these shapes are changed by about 1%. So the ellipticity, let's say the ratio of semi-major to minor axis is changed by percent level. However, what you can do is you can say take all the galaxies in this square here that I'm outlining with my pointer, and you could average over those. By themselves, they should be randomly oriented. And so the net elongation that you see would probably still be along these lines and hence indicate that we've got here some tangential effect going on pointing towards a mass over density up here. And this net ellipticity that you can measure is called gravitational shear. So it turns circular sources into an ellipse to first order. The size, the apparent size is also changed. That's called magnification. That's a bit trickier to detect. So we mostly focus on this shearing effect. Okay, and again, you see the same thing. Try it out with your wine glass tonight and you'll see the same effect. Now, we can use that over very large areas. We do a big galaxy survey. We look at the shapes of millions, and in future with Euclid, billions of galaxies. We look at the shapes. We do clever averaging over the sky in a very careful manner. And then we can indeed reconstruct where along the line of sight we would have overdensities, where mass really starts to deflect the light, where we have underdensity, where the opposite thing happens, where light rays are pushed outwards. And average densities where nothing would happen. And doing that, we can then reconstruct projected maps of the matter density. And you see an early example of that here. So the colorful contours here in reddish hues is the density, the projected density of total matter, and most of that is dark matter. We see here in certain parts of the sky. So this would be right ascension and declination. And you see here this sort of network web-like structures, which we call filaments. And we see big holes in the middle, which we call voids. And you see where we have the densest areas, so where we've got very light, lightish hues, so you do see big white circles. So the circles are average concentrations of light. So you take all the galaxies, collect their photons, and calculate the size of the circle according to how much light they've sent us. And the important thing that you see from here is that light follows the mass. Okay, so we see here where there's lots of matter over density, we also have lots of galaxy light coming in. Here, for instance, very obvious. Conversely, where there's no dark matter, there's hardly any galaxies either. So indeed, the galaxies are like beacons that sit on top of the darkest portions of this dark matter cosmic web, as we call it, behind it. And to give you an idea, I failed to link this to my slides, but I'm now going to do the experiment of quickly switching, which might badly fail, but let me try. What happens now? Ah, you can see it. Okay, so if I hit play now, if we're lucky, yes. So this is a graphic from an N-body simulation, and it happens at the start. Let me just go back to that and hit stop. So we start with an early universe setup. It looks like randomly distributed particles in there. There is actually a bit of structure in there, as would be imposed by early universe physics, like inflation, for instance. What you see up here is redshift, so it's actually already relatively late. Initially, the structure develops very, very slowly, and it's difficult to see. And then as we switch on essentially time steps and go forward, we just have classic gravity acting on these particles, like normal Newtonian physics as you learned it at school. And as all these particles interact, you see these very interesting patterns evolving. Very quickly, you see the cosmic web appearing. So filaments going across, and where they intersect at the nodes, you have particular overdensities. And this is where you would have massive galaxies and galaxy clusters forming. So indeed, this cosmic web structure is traced by the galaxies themselves. However, the dark matter we can directly map, at least in projection, using this weak lensing effect. Okay, let me go back to my slides in the hope that this works well. Just a sec, I need to get the presentation mode again. How do I do that? Aha. That looks good. Now I need to share it again with you. Aha. There we go. Okay, whew, that worked. Right, okay. So we actually can now make maps of dark matter. We can see dark matter using the gravitational lensing effect. Now we can do more, as I just mentioned. We can also observe the galaxies themselves. And so the sketch that you see here in the top left illustrates that. So this is a wedge actually of real observed galaxies. This is from the Sloan survey. And you actually can see the filaments in the distribution of the galaxies. You see these elongated structures. You see the nodes where the clusters are. Now, what we can do is we can measure the weak lensing effect, illustrated by this rather exaggerated wavy line. So there's a background source here, and the light gets continuously deflected by all these structures. So we can make maps of that distribution directly. You can observe galaxies themselves, as the Sloan survey has done here, and we can trace that pattern as well. How the tracing works is not quite trivial, but the key thing is we do this in the same volume. We do this jointly in the same part of the sky. And together, the clustering and the lensing become a very strong probe of the cosmology here. To give you an example, for the clustering, you see this rather unassuming plot here on the right-hand side. Now, what that is, it shows you the excess probability of finding other galaxies around a single galaxy. So here on the axis, this S is the separation. So imagine you set yourself on one galaxy and you count how many galaxies are at a distance of, let's say, 50 megaparsecs of H, that would be here, or 150 megaparsecs, and you just plot the count that you get. That's what's done here. And at around 100 megaparsecs of H, just above that, you see this interesting bump. That means there is an excess probability of finding galaxies at this typical separation around other galaxies. And this happens due to early universe physics. It's actually pressure waves propagating through the baryon photon fluid in the early universe, which then suddenly stops when the photons decouple. That's the formation of the cosmic microwave background. And then this scale is frozen into the large scale structure. And we can observe that at different redshifts, at different epochs. Now, as illustrated here in the bottom right, you can use that. Essentially, you now have got a standard ruler, because you know from early universe physics, this has to be at 100-something megaparsecs. So you observe a known length scale under a certain angular separation that you see on the sky, and just with simple trigonometry, you can work out what the distance is. You can do the same thing at different redshifts, and you can do it all the way to the cosmic microwave background itself. And that gives you a very good idea about how distance, look-back distance evolves, and that tells you about the geometry of the universe. So you can use the clustering for that. It's a very clean way of measuring this. On top of that, you see these red arrows here. We can also, with a trick, observe how these galaxies move through the universe, through the cosmic web, as they keep assembling, so as they keep falling towards the largest overdensities. We can do this along that line of sight, and it leads to small changes in the spectra of the galaxies as we observe them. And this trick to extract that is called redshift space distortions. And I've sort of illustrated here with a sort of traffic light system where the colors correspond to what I labeled up here. So blue is weak lensing, it's this shear effect. Yellow is the clustering with the BAO scale, this bump here, and red is the redshift space distortions. And the different things that we can measure by this. And the key again is it's the combination of them that does really well. So for the amount of dark matter, weak lensing is good at that, but also this BAO measurement, because distance is also affected by how much dark matter there is. It determines the expansion history, and that impacts on the distance. Dark energy, I haven't mentioned so far. The only impact dark energy has, because we think it is smooth, is that it changes the geometry. But as I said, we are sensitive to it, for instance, through measuring this bump here. And weak lensing has some sensitivity as well, because essentially your lensing effect depends on the distance between you, the lens, and the source, just like in normal geometric objects that you did at school. And so there's a sensitivity in weak lensing as well. And again, the combination helps us to distinguish all these different effects. The clumpiness of dark matter, weak lensing is really, really good at doing this. Redshift space distortions also help us. The clumpier, the stronger the galaxies will move towards over densities. And then looking at the growth over time, averaged over time, this is really the realm of these redshift space distortions. But again, weak lensing, by doing it tomographically, meaning looking at different slices of galaxies and measuring their lensing effect, is sensitive to that as well. So the key thing to telling all of these effects apart is doing these measurements jointly in the same cosmic volume, in the same part of the sky, and ideally in one comprehensive project that does all of this together in a uniform way. And that is where Euclid comes in. Euclid is going to do exactly this. So finally, I can show you real pictures. Up to now, I just showed you the fancy images on the left. The right-hand side is now the real Euclid in the lab. Well, it's still cheating a bit. This is not the thing that will be shot into space. This is the thermal and structural model, so the thing that you heat up and shake about to make sure that it doesn't fall apart. Here I've got a sort of cheat sheet by the PI of the Euclid consortium. No need to go through all that in detail, but just let me give you sort of the highlights. I updated some numbers. We plan to launch in June 22. We're going to have a virtual consortium meeting next week where I'm going to find out whether that still holds. That was all before the whole world got shut down. It's going to be sent out from Kourou to Lagrange point 2, which is outside, so on the opposite side of the sun from the Earth, where other deep universe missions like Planck also were sent, nicely shielded there from the sun, and we can look out in relative peace there. You see Euclid here is mainly a telescope, of course. It's about 1.2 meter in the primary mirror. And below here, you see what we call the payload module. I'll show you a nicer picture of that in a moment. We have two instruments there. One is called VIS. That is like, well, it's essentially one of the largest digital cameras that have ever been put into space. It's going to do optical imaging and going to have very, very high image quality together with the optical system. And that allows us to measure these tiny distortions of galaxies for many, many of them. You see some interesting structures here, like for instance, the shutter. All has to be designed very carefully. For instance, if you've got a shutter that just quickly moves, you create angular momentum, and that will start to move the telescope and destroy your high accuracy in pointing the telescope. So all of this has to be thought through very carefully, obviously. The second instrument is the near-infrared one. That's going to take spectra that helps us to pin down where the galaxies are. So that's important for the clustering, but also some extra photometry that helps us to find out where galaxies are along their site, how far they are away. Euclid follows the philosophy to do only from space what has to be done from space. It's only a medium-class mission after all. So there will be ground-based data that does optical photometry coming in, all entering this infamous acronym here, the SGS, the Science Ground System. It consists of many of these flowcharts. So this is where the whole processing of the data from the ground, from the telescope in space takes place. And in the end, you should get out very nice science. This is a very complex business that is most of my day-to-day work, and it has been going on for a long time already. What we'll have in the end is about a 6-year survey that will cover 15,000 square degrees. It's essentially the whole extragalactic sky that we can reach. You see two black stripes here. One is the galactic plane, and the other one is the ecliptic. In the ecliptic, we have a lot of background from interplanetary dust. This is how sensitive we are. So this is our main limiting factor, that sunlight scattered off interplanetary dust limits the way we can look into the universe. Right, moving on, some nice pictures, very recent ones that you see. This here is, again, the payload module. You see here, this is the infrared detector NISP. This is the VIS detector, the big camera that we have. So this is now excellent upside down. You see the telescope down here. The primary sits here, the secondary up at the top, and then the light comes through this hole here. It's going to be reflected here, which I believe is the tertiary. Yeah, should be. Then we've got a dichroic that you can see. It splits light beam. Part of it goes into here, the infrared part. The visual gets bumped off at this. This is just a folding mirror, and then it goes into the VIS camera. And there's some calibration lamps and all that on top of here. So it gets quite busy in total. The actual cameras have been delivered. Fortunately, just before the shutdown, this is a picture of the infrared detector. So it's this bit here. The primary is all there. You see, it's actually not such a big telescope, 1.2 meters. Some amateurs have larger telescopes in their back garden. It is a small space telescope. It's really all about the quality, and it's got a relatively large field of view. So it's quite efficient in capturing large parts of the sky. And you see here, this is the service module or the casing for it. The service module then contains more the sort of the boring things like batteries, communications, and electronics. Right, just a very brief highlight. I think I should wrap up fairly soon. About challenges, there's a long list. I could give a whole talk of this, of course. Just to give you a flavor, at a sort of very, very image-like level of what the challenges are. This rather ugly picture that you see here in the top left is actually what the spectroscopy is going to look like. It's slitless. You might be used to beautiful images with fiber spectrographs that have high multiplexing, but you need to position the fibers, and moving things in space are usually a bad thing because they might break and you cannot fix them. So what we have here is just a dispersing element that goes into the whole field of view, and everything that is in the image is going to get dispersed. So all the lines that you see here are the spectra of whatever you get in there. It could be a star, it could be an asteroid coming through, or it could be the galaxy that you want. And of course, they all start to merge, to run into each other. So you have a very hard time telling which part of the light in this part of the spectrum belongs to which object. And so we have to find clever ways of telling these hundreds and thousands of spectra apart. And one way, of course, is to rotate this dispersing element. So that we have actually several dispersing elements on board, and the filter wheel, which is the one moving bit, is going to rotate them in, and then we're going to get dispersion in a different direction. And hopefully then we can use algorithms to tell the spectra apart. On the galaxy shape measurement, so the shear measurement, to give you an idea just of how hard it is. So this would be a true image. It's hard enough to tell on these galaxies what you would call a shape, right? The shape changes depending on at what scale you look at in this galaxy. But to make it worse, we have to look at very, very faint objects. So what you actually see is something more like this, right? So these beautiful galaxies turn into blobs, pixelated, noisy blobs. And now what is the ellipticity of this object? By eye, it's impossible to say, and you have to be very careful about this. And you have to do this to an accuracy that is 0.2%. This is the requirement for Euclid. This is why it took us a decade just, well, to get this ready. Frankly, we're still not ready yet, so it's a really difficult measurement. To make matters worse, if you put a CCD camera into space, it gets bombarded by cosmic rays. And so initially, you may get nice pictures like this, but over time, it will start to look like here on the left-hand side. You get these trails. The cosmic rays essentially damage the CCD, and that creates buckets where photons get trapped. And then they get, as the CCD is read out, they get slowly smeared out, creating these rather ugly trails. Now you're trying to measure an ellipticity of objects, and by doing this, you have created a very obvious ellipticity, which of course is vertical in this case. So this has to be mitigated and corrected. It's an effect that will get worse over time as Euclid is up in space. And we need some very good understanding of CCDs and some very clever algorithms to correct for this. There's many more things that I could talk about, but let me finish with a sort of science sneak peek of what Euclid might be able to do in actual practice. This is an analysis that I happen to be heavily involved in. It's using precursor data. There's the ESO Kids survey, which does weak lensing. And this is the BOSS survey, it's a Sloan survey that did galaxy clustering. So again, the same kind of data that Euclid will collect. And if you, after very long and careful analysis, combine them, you get constraints that are shown here. So the dark bit will be a 68% credible region, and the outer one will be 95%. And you see here the clustering would be the reddish constraint, and the dotted lines here would be just lensing alone. If you combine them you get to these rather nice green constraints here. I should say what the parameters are. This is dark matter density parameter. So this is essentially how much dark matter is there. It's actually how much total matter in there, but it's mostly dark. And this is the clumpiness. So the higher this value, the more clumpier the large-scale structure of the universe is. And the intriguing thing is, if you make a measurement in the early universe from the cosmic microwave background, as done by the recently completed ESA Planck mission, fantastic experiment, very precise. And if you then extrapolate their constraints from the early universe to today, you end up at these blue contours. And as you can see, blue and green disagree. Planck thinks that matter today should be clumpier than what we actually see. And this effect is now that such that, let me just do that math in my head, that it's about a sort of few per mil, 3 per mil chance that this is just a statistical fluctuation. So in other words, a 99.7% chance that there's some systematic trend going on here. We have no idea what that could be, but it's exciting. It could be a sign of new physics. No good idea what that could be. But again, it could point us to other problems in our cosmological model, or it could be that we're missing something major in our observations. It could be on the clustering and lensing side, or it could be on the cosmic microwave background side. Again, we don't know what that is, but a lot of people are now very excited about this and trying to find out. And of course, Euclid will shrink these contours. It will have sky area that is up to an order of magnitude larger. It's going to shrink the green contours to a very small point, and then we're going to know for sure what's going on. So a lot to look forward to. I'll end here with a quick summary that I leave out there, and you see a picture of this rather large collaboration. Euclid is one of the, if not the largest astronomical collaboration that ever existed. It's about 1,500 people on paper, and at the meetings, when they're allowed to take place in person, you have typically about 500 people there. So it's a big effort of the community. We're very much looking forward to flying the thing in a couple of years' time. I'll stop here. Thank you.
Thank you very much. Thank you very much for a very nice presentation. Very interesting from a couple of the points. And I mean, we will address probably those points in the questions part. So please stop sharing your screen and I will share the Slido. Okay, thank you very much. Yeah. And second, let me, okay, here we are. Now, okay, now we could see Slido. Okay, so fine. Okay, let's see what, 14 questions. Okay, so please, I encourage everybody, you could vote and you could put another questions also to connecting to this one if we will not fill everything. So let's start with the most popular one. So, well, how likely is that dark matter is not a particle, but something macroscopic, something like brown dwarfs, invisible population of brown dwarfs, primordial black holes, or something else? How likely it is?
Yeah, at the moment, I would say it doesn't seem very likely. So the techniques that I described they don't care so much for the nature of individual objects or particles. What we get from these is more global properties, like the abundance, maybe cross-section, interaction cross-sections, so these global properties. Now, but even so, we've got other measures to combine with to find out more. For brown dwarfs, I don't think I'm up to speed with that. I think you would need to really mess a lot with initial mass functions in galaxies to have such an excess of low mass objects. Mm-hmm. So I think brown dwarfs are difficult to explain all of this. And yeah, I doubt that this would be possible. For instance, you would need a lot of brown dwarf populations in the outskirts of galaxies, mm-hmm. Where you don't have massive stars anymore. So there's no reason why this mass function, stellar mass function, would evolve so dramatically as a function of radius. So I think brown dwarfs would be very difficult in this explanation. Primordial black holes, however, have had a bit of a renaissance recently. Mm-hmm. So by the time Euclid was selected as an ESA mission about 10 years ago, everyone would have betted on WIMPs, weakly interacting massive particles. So a new particle that is stable, that is relatively heavy, and essentially does gravity, but not much else. So that's the perfect dark matter candidate. And people had a good idea of what it could be, namely the lightest supersymmetric particle. And the LHC was supposed to find it. The only problem is they did not. So it would have been in the range of 100 GeV, and it's simply not there. So now you have to have either more complicated supersymmetry theories, but I hear from my particle physics colleagues, they are not that keen about that either. So we don't seem to have a good WIMP candidate. And now other ideas have come up again, and including primordial black holes. However, now a lot of people have scrambled together to put constraints on this. And essentially you can now, over a very, very wide range, if I remember correctly, something like 10 to the minus 10 solar masses to hundreds of thousands of solar masses for primordial black holes, you can now exclude primordial black holes down to at least 0.1, and in many cases even to percent level. contributing to the dark matter, which means that even if primordial black holes are there, they are not nearly enough to explain the dark matter phenomena that we see. And the constraints are manifold. There are probably a dozen experiments that do this. For instance, at some point they need to produce X-rays in the early universe that we don't see. At some point they could mess up early universe physics. That puts a constraint, and so on and so forth. So although it's a neat idea, the possible parameter space essentially has been excluded over the last few years. So nothing macroscopic as a hot candidate for dark matter at the moment.
Yeah, so I will little bit ask more about this. So you generally, I know it's hard to say, but generally you think that this macroscopic option is less or more probable than, let's say, 1% or 10%? What do you say? It's really unlikely, or it is like, I don't know, 10%?
Yeah, I wouldn't bet on it, but I would say it's closer to the 1% at the moment. Okay. So for instance, more popular these days, axions are quite interesting. So they would be extremely light dark matter particles, but with very special properties that make them look like they are like cold dark matter, so with low velocities. That seems very interesting, and there's some theoretical motivation behind it why axions should exist. They are, however, extremely difficult to find. So what we really need is help by our particle physics colleagues who look at direct detection experiments to give us a hint of what the particle could be. And so something like axions, for instance, seems like a very interesting candidate at the moment.
Yeah, now let me also ask that. So my understanding is that you are thinking that, let's say, the Pamela IMS02 measurements of the positrons excess is unlikely to be a sign of dark matter. Did I understand you well, correctly?
Yeah, again, I'm not an expert on that area, and I might not be up to speed either. But all I can say is we have the direct dark matter detection experiments like LZ, etc., and various others going on, and we have ideas about sterile neutrinos that are still around. So I'm not sure how those are being chased, and I've heard of experiments that want to go after axions, and again, I don't know what the technique is. They seem to be extremely elusive, so I can't say about how they're trying to target it, but there's certainly an effort going on, so it is happening.
Okay, so thank you. Next question. Well, this is referring to YouTube video about Euclid. So in one of the René Laureys, sorry for that pronunciation, YouTube videos about Euclid, is mission described as most accurate telescope ever built. In which parameter is most accurate?
That's a good question. I'm not sure what René was referring to. So I should say René is the project scientist working at ESA, so he certainly knows what he's talking about. If I can hazard a guess what he was referring to. So one of the key drivers, if not the key driver, is indeed the weak lensing measurement. And as I said, we have to measure shapes of very noisy faint objects to this ridiculous accuracy. And in order to do that, we need to understand exactly what the telescope and the detector does to the photons as they come in. So the optical system that starts with the mirrors, Euclid is a 3-mirror telescope, and there are other optical elements in between. The dichroic, for instance, that splits the light ray, is a particularly troublesome object in there. All the way to the detectors themselves, what they do with it, this charge transfer inefficiency, this sort of light trails that are created, all of that needs to be understood to extreme precision, much more than has ever been done. And in that sense, the requirements that we set on the telescope have been more stringent than for any other space telescope in existence. Hubble is comparatively crude compared to what Euclid needs to do. Of course, it's a larger instrument. So I think René was referring to this. So it's in terms of the accuracy of understanding the optical and detector system, in particular on the optical side, that I would think is here. For instance, to give you an example, we actually plan to model the point spread function, right? Usually we observe stars and say, well, okay, that's what the point spread function looks like, and then we go with that. Since we don't have an atmosphere that keeps constantly changing, with Euclid, actually, we think we understand the whole optical system, everything that happens to a bunch of photons coming into the telescope so well that we can build a forward model of the point spread function completely. That has never, to my knowledge, has never been attempted before.
Aha, so maybe if you look to the moon, what the details you will see there.
Yeah,
Would
yeah.
you
I'm afraid
say?
the moon is way too bright. Yeah.
Okay, yes. Okay, so let's skip this next question. Okay, so Euclid is called a data-driven space mission. 100 gigabits per day is impressive. Yes. What will be the data policy, in which form, and when you will publish data? In catalog?
Right, yes, so that's a good question. I didn't refer to that at all. So again, to put this into context compared to other experiments that are about to come, like the LSST or the square kilometer array on the radio side, Euclid is comparatively benign in terms of the data rate. So it can be much worse these days. And we're actually limited by the data link, so of what the telescope can send down to the ground stations. Now, what Euclid is going to do, there's a lot of processing going on. To give you an idea, if you completely say, oh, I want to rerun all the data all the way to the data products that astronomers will be interested in, that takes about 6 months, we reckon, just the processing. And so Euclid will work in total 3 data releases. There will be sort of some quick view data in between, but the main chunks will be in releases, and there will indeed be the raw images and catalogs with derived products. For instance, redshift estimates for galaxies, shapes of galaxies, spectra of galaxies, where we have them, all of these. And then there will be higher level data products that will be produced by the consortium, for instance, cosmological measurements of power spectra, summary statistics, and even constraints. And these data, the first data release will be, oh, let me do that in my head, about 2 years after launch, maybe a bit less than that. So they're well defined. And then we'll have 2 more data releases. The final one would be in 2028 at this point.
Yes, it's similar to Gaia.
Yeah, I think so. I think so. Yes, indeed. So Gaia is a bit different in the way that the collaboration structure works. So Gaia is really committed as a consortium to produce the sort of main solution, astrometry, proper motion, all that is going to push that out. Euclid will take a step further. We're not just going to produce the data products. We're also going to do the main science analysis and then make that public as well. Of course, it still allows you to do whatever exercise you want to do, because it's going to be an extremely rich legacy data set on top of it. So in that sense, Euclid even adds another little extra step afterwards to it.
Okay, thank you. Well, this is a nice question. Are there some tools, data, or databases for user of Euclid data available already? So to train and learn to work with Euclid data in advance?
That's indeed like that. Yeah, that's indeed a good question. So to the level that you have a lookalike of Euclid and can play with it, not yet. What is there already is the Euclid flagship, which is one of the largest n-body simulations ever run. If you go back to the last slide, the summary slide, the top band there is a slice out of that simulation. It's very, very large, and then there are new versions being produced at the time. And it has realistic mock galaxies that look like the Euclid sample as well. Earlier versions of this have already become public. So in that sense, you already can start playing with this. You have a mock galaxy catalog that will look like Euclid, has realistic underlying cosmology and dark matter distributions in it. So that gets you close. It's not going to have the format, for instance, that the Euclid catalogs will have, because I can tell you they haven't been properly defined yet. We're still in the process of doing that. What you're probably looking for, like a tutorial and like example access to the ESA databases, I think that would be very useful to have. I hope this will happen, but it hasn't happened yet.
And how big is this one which is already public?
I can't tell you in terms of bytes at this point, but let me see in terms of. No, I don't have the numbers to hand, I'm afraid. But at the time it was run, which is by now 3 years ago, it was the largest embodied simulation ever created.
Oh, okay.
So it's indeed the full Euclid sky was covered.
Thank you. Next question is a question which every speaker answering in this series of the webinar. So, if you could have a budget like James Webb Space Telescope, approximately $10 billion, what space mission experiment you will like to see to become reality?
Right. Okay. So that's about an order of magnitude more than Euclid actually has. So what would I do? I would, of course, try to turn Euclid into a fantastic space observatory. So we had to make a lot of compromises to fit into the budget, like every space mission has to do. So I would certainly want to reinstate a few things. I can give you an example. So on the weak lensing side, the way we get to the depth that we need with the 1.2 meter telescope, which is again not that big, is that we have a very broad filter in the optical. It's actually not a filter at all. It's just the transmission is defined by the optical elements itself, like the mirrors. That creates all sorts of problems. For instance, if the color of your object, right, evolves within this broad spectral range that we're sensitive to, then, for instance, your point spread function will change. In space, it's driven by the natural resolution limit, and of course, that's a function of wavelength. That is causing a major pain for us. So if we could split our broad transmission into 2 or 3 filters, all of these problems would go away. And we could even take a step further and say we do all the photometry from space, which is much more stable and uniform in the same system, rather than piecing things together from the ground. You have to bear in mind, Euclid is observing the whole sky, so you need experiments in the northern hemisphere to give you ground-based photometry. You need another experiment in the southern hemisphere to give you that. And they're all different telescopes, different cameras, different observing conditions, etc., etc. So it's a massive enterprise that we have to do because of these limitations. So I would certainly want all that. In order to achieve it, I need a larger primary mirror, so I need a bigger telescope. And then my friends on the spectroscopy side would certainly appreciate more of these rotations, so more observations of the same part of the sky to help them tell apart these various spectra, slitless spectra. So all in all, it would look a bit like the Hubble Space Telescope, but with advancements in the instruments by 40 years.
Super, Euclid. Okay. Okay, thank you. Next question. What is the most challenging part of Euclid telescope technology? What was or will be most hard to develop, to build?
Right, so most things have been built in terms of the hardware, so that's been done. So I can look back of what proved or is still proving to be quite challenging. So to make Euclid work and this very busy payload where we put all the instruments, there was a base plate made of carbide, so very light material that keeps us within the weight limits. That, again, I'm not an expert, I'm not an engineer, that apparently was quite hard to do, and the first version that they had split right in the middle, so they had to do it again. So this seems to be one of the largest, most complex pieces, and you have to put them into a mold apparently, and then they form that way, that were ever built. So that's on the pure engineering side, quite hard. Somewhat more on the technical side, both detectors, so the infrared detectors and the visual detectors, again, are quite unique in the way they work. They had for a lot of time problems getting the infrared detectors to fit into the requirements. This is the US contribution to Euclid, so they're provided by Teledyne, and they essentially had to completely redesign the infrared detectors, which amazingly they managed to do within the time frame. So that's all doing fine now. Also on the Viz side, it's performing extremely well, but just validating it, showing that it actually has this capability is extremely hard. In the lab, it's not easy to create something that looks like distant starlight. And so it is quite amazingly difficult to get this right. And if I interpret technology a bit more widely in terms of measurement, there's a conceptually very simple problem that affects all astronomers, and we're hit by this as well, namely how far away is that object? So for the vast majority of galaxies, we will not have a spectrum that tells us the redshift. We have to guess what redshift they are and what distance they are. And that turns out to be a major issue. Just like it was 500 years ago, it's extremely difficult to find the third dimension. And again, this keeps a lot of people busy to figure this out. We use the multicolor information, including the information from the ground, to get something that we call photometric redshift. that has a lot of scatter. There are a lot of failures if you misidentify pieces, and how to calibrate this and correct for this is an open issue.
Thank you. Thank you. Next question. Oh, that one is funny. Years ago, I visited a dark matter conference, and my impression was that there was 100 dark matter physicists, scientists, with 200 theories what dark matter is. Is it still the same?
Yeah, I'm sure the creativity of our theory colleagues has not diminished since then. Now, from my sort of somewhat outside perspective, as someone who analyzes the data and then gives that to the theorist and says, does that match anything you've got in your drawer? My impression is that there has been movement there. So I don't think the number of theories or ideas has gone down, but there's been movement. And I already mentioned this. So 10 years ago, it was WIMPs, that everyone would have bet their money on this. I think that has largely evaporated now. Primordial black holes, as I mentioned, had a sort of resurgence, and then people jumped on it and constrained it, and there's a lot of great work going on. And it seems like that's slowly dying its death as well, because it's just experimentally excluded, although it's a neat idea. And so now, yeah, where are we now? We had modified gravity theories. They were popular over the last decade. So things like MOND and generalizations thereof, so modified Newtonian dynamics. The idea is dark matter, you just invented a sort of epicycle because your theory of gravity, the one that Einstein came up with, isn't quite right. You need to modify it, especially sort of long range behavior. Again, neat idea, and it's nice if you don't need to have an extra particle around. However, again, that the easy forms have all been disproven. They don't work. They're very general theories that invent lots of extra fields, and they have so many knobs and twists that they can't even make predictions. So there's not much we can do about them. There are interesting new ideas that I have barely heard about. There's non-local theories of gravity. So you have a non-local component in your gravity. And that indeed, some phenomena of this could act like dark matter does. So maybe people haven't quite given up on getting rid of the dark matter particle as such at all. But the mainstream is there has to be a particle, and then axions, as I mentioned, is an interesting and sort of theoretically grounded way of explaining that. But they're very difficult to measure, so they will be around for some time either way until we can pin them down.
Yeah, but okay, what's your bet? In 10 years,
in 10 years.
You know what is the dark matters? Most hard question, yes. Just
yeah.
What's your
I mean, I'm not in a, frankly, I'm not trying to chicken out, but I don't have enough to even put a bet on anything at this point. I mean, we have these fundamental issues. We have this beautifully working cosmological standard model that has these major issues in that 95% of the stuff that we put in, we just have to make up more or less. And that's particularly true. I mean, dark matter is one thing. That's at least concrete. But dark energy is even worse. Because we have the cosmological constant that just another free parameter that causes a lot of problems with coincidence and all that. Vacuum energy would make sense, but it's orders of magnitude, many orders of magnitude off. So we somehow would have to null this and let a little bit of it back in. And all these other alternatives, they have major issues. So there's nothing appealing to me that could explain this. But I think what we would need is a completely new ansatz to solving this, which essentially means replacing general relativity. And I think we are decades away from doing that. I think this is really, really hard to do. And so I'm afraid that during our lifetime, and I include everyone in the audience here, we might not see that revolution happening. So if I have to put a bet, if I have to put a bet, and it's a pessimistic one, then I would say we're not going to find the answer unless someone someday comes to us and say axions are actually there and they do exist. Then things change, something like that. If that does not happen, we might be stuck with this for a long time. We'll get more and more clues, like these interesting discrepancies that we're seeing now. Euclid will tell us for sure whether that's real or not. That will guide the theorists, but until they've made use of that, that will take a long time.
Thank you, clear. Okay, now another question, technical one. What programming language or framework is used to build Euclid software?
Right. Okay, that's easy to answer. So there's the sort of gold standard that we have all across astrophysics these days. It's Python and C++. So we use C++ for things that have to be fast. And so at the top level, we all use Python.
Thank you. Fine, another question, next one. When people from Euclid Consortium say that they want to make decisive measurements of the accelerated expansion of the universe, what do they exactly mean?
Right. Okay, so the headline that we want to do is, we know, well, we know from various experiments, including weak lensing by now, is that we do indeed have this accelerated expansion. We detect it with significance, but we want to see whether it's a fluid, it's a scalar field, or whether it's really just a cosmological constant or something that works like it. One easy way to tell this apart is looking at the equation of state. So all the constituents in the universe, like dark matter, like radiation, so relativistic matter, curvature even, they can be characterized with an equation of state parameter. That relates essentially the overall pressure of the component. So it's essentially its velocity and thermodynamic components to the density. And for dark energy, this would be -1, this particular quantity. Now we can check whether it really is -1 or whether it deviates, and we can also check whether that changes over time. If it does, it tells us it's something dynamic, it's some fluid, it's some scalar field that permeates space. That would be a major, major hint. And by the way where it sits, whether it's less than -1, you get really bizarre stuff then, or whether it's a bit larger than -1, that's less bizarre, and how it changes over time, that will give us a hint of what could actually be going on. This is what we mean by it. This is how Euclid has been designed to measure the equation of state and its redshift evolution.
So this is real experimental cosmology. Real. Okay, so thank you. Another question. How big is 23 petabytes processing in comparison with other space experiment, other space science experiments? Are there space experiments using more data? Do you know if there are some more?
No, yeah, that's a very good question. I don't know. So ground-based data is easily producing much more than that, but they don't have the problem of having to downlink the data. So it would be interesting to know what, for instance, JWST does. I was just wondering, is there anything else? No, I'm not aware of it. So for instance, if you go to an ESA L-class mission, you might be able to afford a larger antenna, and then you can have a larger downlink rate. I think Euclid is pretty much at the top of what an ESA M-class mission can do. That's all I can say, just from experience.
Yeah, anyway, it's pretty big amount of data. Okay, thank you. Well, another question. Would you consider the mission to be your magnus opus? Are there already any plans or proposition for future mission after Euclid you will be a part of?
That's a good question. So Euclid will certainly keep me busy for another 10 years. So even if we don't pick up further delays until all the data is analyzed and published, we're clearly looking at 2030. So it's not like I have to make immediate plans for something else. Now, I am also involved in a ground-based large experiment, which is the LSST, used to be called the Large Synoptic Survey Telescope. It's now called the Rubin Observatory, and it's the Large Survey of Space and Time. I had to retrofit that acronym. So that's a ground-based experiment, extremely fast. So the data rates are astounding for that measurement. And it's also going to run roughly on the same timescales as Euclid, even longer into the 2030s. It's going to be highly complementary to Euclid. It's going much deeper because it's a large telescope, but it does not have the resolution from space. And so one of my grand plans is to actually combine these data sets, as here in the UK at UCL, we're one of the few groups who have access to both, and we are heavily involved in both. And so that's clearly something I want to do, and that would take me beyond Euclid. On an even larger time scale, again, I haven't made any commitments yet, but to give you an idea of where this whole area is going, of course, gravitational wave astronomy is going to open up a major second channel into the universe. LIGO, as exciting as it is, it only has the local universe. It goes out to redshift 0.1 or so not really the redshifts that we care for. But LISA, which is going to be an ESA mission probably in the 2030s, is going to change that radically. So that would be the next step. It's going to look out into the deep universe. You can even do gravitational lensing of gravitational waves. So I could continue doing that. And then a final version, a final status of the speculometer array, as they build more and more antennas, will also start to look into the deep universe, and it will solve a lot of problems that we have in the optical. You can essentially design your image to look like you want it to by reconstructing it from the phased arrays, and you can essentially get a precise redshift for every object that you can detect with the full SKA. So that would be super exciting. And again, that's something that will happen well after 2030. So this could be future directions where I could see myself going.
Thank you, thank you. A lot of things to do. Let me note that we will have in 1 month, we have webinar of LISA mission with Paul McNamara. Yes, I think so. So you could check on this web. So this is also very, very nice webinar we are looking forward to, but let's continue with questions. So, how your typical working day? What was the most of the time?
Yeah, okay. Well, all in all, I've got a teaching position, so a lot of my time is actually spent on teaching undergraduates and looking after my PhD students, etc. So that needs to be taken into account. A large fraction of the remaining time is indeed spent on Euclid, and it is managing a part of the ground segment. I'm responsible for validating the final weak lensing data products. So I've shown you this example of a map. We actually, in quantitative analysis, we don't use the pretty map. We actually calculate statistics on that map. And this is one of the key final products that Euclid will produce that will then be used in the science analysis, and they'll also be made available to the public. And so I'm in charge of a number of postdocs and technicians who try to set this up and then make sure it actually is at that very, very high level of precision and accuracy that we want it to be. I'll try to do a bit of science as well. I'm in charge of a group that looks at intrinsic galaxy alignments. So some nice astrophysics going on in there. And it's simple to understand. I mentioned earlier that we use this trick of averaging over many galaxy shapes, assuming that the intrinsic shape of the galaxy is more or less random, and the net effect that remains is our cosmological signal. Now, I made that statement, but it's not true. So galaxies have the somewhat annoying tendency to align with each other due to tidal fields, again, in this filamentary structure. So galaxies, for instance, that live along the same filament, they tend to have the same orientation. And this is what's called intrinsic alignment. So I'm leading, coordinating a group that tries to find out an astrophysical model of how these alignments work. And there's a lot of fun, complicated galaxy evolution going on in there that we have to put into our analysis to tell it apart from the cosmological signal. And so that science-wise is very interesting to me. And then my remaining time is on working on precursor data, learning from that data, and then transferring that onto Euclid and LSST, so we learn for the next generation.
Yes, thank you. Because I will connect another question to this one, because most of the audience are students of technology. What is the role of machine learning in this? Because you mentioned machine learning in your bio.
Right, okay. Yes, it increasingly plays important roles these days. So I can give you a few examples. At the highest level, at the inference level, we need to do likelihood analysis. So essentially, we do fitting. Chi-square fitting is maybe something that everyone has encountered at some point in the undergraduate studies already, or maybe even at school. So we try to fit a curve, a model, to a set of data points that have error bars attached to them. Now that seems reasonably straightforward, but if you want to do it very, very accurately, you have to be very careful. Our models are very complex. We've got dozens, maybe in future, hundreds of parameters. And how you do a minimization over this parameter space is actually surprisingly complicated. And there are no general solutions to that. And so actually astronomy and fundamental physics have always been at the forefront of finding ways to explore this MCMC, Monte Carlo Markov chains, is a classic example that has been around for more than 50 years and has gone into many other fields since. But that was originally conceived actually by the people who worked on the atomic bombs. Similarly, we're still trying to understand new ways of inferring parameters from these very complex data sets. To make matters worse, error bars are not enough either. Error bars work very well if you've got an underlying distribution. Statistical distribution is a Gaussian, because a Gaussian is characterized just by a mean and a standard deviation, which is the error bar. But if this distribution becomes skewed or has kurtosis or starts to look boxy, or even has secondary peaks, this whole matter becomes much more complicated. And so on this sort of statistical side of things, I spend a lot of my time. And machine learning comes into effect as well, for instance, in terms of emulators. So we try to speed this whole process up by learning, by having efficient ways of learning connections between parameters. And to give you another example, at the complete other end, very close to the actual data, there are some very complicated patterns, for instance, the patterns of the point spread functions across the field of view, or of background light in the field of view. And in the past, we just modeled that with polynomials and essentially crossing our fingers and hoping that it's not going to blow up at the edges and be fine. You can do a much better job by training a neural network to learn these connections. And since you've got images, you've got very high redundancy of the data, so it's perfect for deep learning, right? Deep learning wants lots and lots of input training data, and you have that at the pixel level. And so you can use deep learning to understand these patterns and then make these corrections much more accurately than we used to.
Thank you. Well, another question. The velocity of the universe expansion was measured by Planck, 67 kilometers per megaparsec. Measurements by supermass candle give 74 kilometers per megaparsec, another value. So could Euclid clarify it?
Yes, not by
still open question, I think.
Yeah, it's not by itself, but in combination with other data sets. So indeed, so Planck, of course, was something that happened in the very early universe, whereas the supernova measurements or others come from the sort of the local distance ladder. So one starts from the local universe, one comes down from the early universe. And the way you do this translation from the early universe, you need some steps that help you along the way. So you need to have a good idea of the model down to redshift 0, where the Hubble constant is measured in the end. We sometimes call this the inverse distance ladder. So you essentially start from the CMB and step your way down. And one way to do this is with these Barrett acoustic oscillation measurements, these standard rulers that I showed, this little bump in the correlation function. And if you measure that at different redshifts, you can essentially step your way down and, for instance, start to look where deviations occur. This has been done with current data, and Euclid will help complementing this, since it's doing infrared observations from space. It's got a unique window on a certain redshift range, which is between redshift 1 and 2 roughly, where ground-based data will struggle a little. And we also have new surveys on the ground coming online. It's the DESI experiment starting just now, that will again complement this with very good coverage over a vast range of redshifts. And with that, we'll have very continuous coverage. So we're going to get a very nice curve as a function of time that will show us how the distances evolve, and hence how the geometry points us to a certain Hubble constant. So in that sense, helping by making that transition, Euclid is going to be very helpful indeed. Weak lensing is not that useful in that regard, at least not the shear measurement I mentioned. There are other strong lensing techniques that are competitive now. If you're interested in that, there's the holy cow, easy to remember, experiment where they use these multiple images that I showed and look at time delays in the travel time. So if one object, say a quasar, flares up in one image, since the travel times are different, the flares will show up in the other images at different times, and the difference is directly inverse proportional to the Hubble constant. So it's a neat alternative way to measure this, and they're getting now competitive error bars. So this is worth looking into. This would be an alternative local measurement of the Hubble constant.
Thank you. Well, last three questions. So, is Euclid consortium somehow different from other collaborations? Do you see something more effective in the organization of your Euclid consortium from other projects we know?
Right. So it's maybe different in that usually, so for instance, if you use Planck had the low frequency instrument and the high frequency instrument, and each instrument had its own consortium and they were doing their own thing. Euclid made the choice early on to put everything together, to have this, it benefits from this joint analysis of different probes on the same telescope, you're looking at the same part of the universe, the same sky. And so this was reflected in creating one large consortium that does everything. So that's maybe different. And that's why the Euclid consortium is so large. That's one reason. The other reason is that Euclid has a very rich legacy. If you've got a cosmic microwave background temperature map, you can do fantastic cosmology with it, but not that much else. Whereas with the Euclid data, you're going to have 1.5 billion galaxies with lots of parameters measured. You can do all sorts of things, all sorts of extragalactic astrophysics with that particular data set. So there's a very rich legacy to it. And so actually most of these 1,500 people in the Euclid consortium, at least the scientists therein, are interested in legacy science rather than the cosmology that I outlined here. So this is maybe different from other collaborations. More effective? No, not really. It's a gargantuan consortium, which is very, very difficult to manage. With all space missions, it has to be rather hierarchical. It's imposed by ESA. And as I think every scientist will tell you, that doesn't go well with the free spirits that we are. So managing a bunch of scientists is like herding cats. And so this is really a struggle. If you have smaller collaborations or even ground-based large collaborations like the LSST, they are comparatively easy to organize in that regard, I have to say. So I don't think there's anything to learn from the management structure of Euclid, rather than you have to endure it.
And please remind me again, how much it is, how much people is in Euclid consortium?
I think all in all, there's 1,500 people registered in it, but that includes engineers, software engineers, actual proper engineers that build the instruments. That's everything included.
And you will have full collaboration list articles, or it's different policy there?
So anyone who is in the Euclid consortium can propose papers and write them. Of course, there are sort of common interest papers, the main cosmology results, some main data papers that will be written by the consortium as a whole. So you will, like in high energy physics, you will have a gigantic author list with pretty much everyone on. Yeah. So these papers
so
are. So
there will be 1,000 names also from Euclid, yes?
Yeah. I
okay.
fear that's going to happen, yes.
Yeah, okay, thank you. Thank you. Okay, another question. To which cosmic ray energies are Euclid CCD more sensitive? Most sensitive.
Ooh, that I cannot answer. That I do not know, I'm afraid. That it would be a fairly broad spectrum, because essentially the CCD detectors for cosmic rays turn into sort of energy dumps. So for a broad range of energies, the cosmic rays are going to deposit their energy in the bulk of the silicon. So I would expect the spectrum is fairly broad, but where it is most sensitive, I honestly do not know. It will depend on the thickness of the detector and how it's shielded, but
shielding. Yeah. Okay, thank you. Last question. How data will be delivered to ERIT? What technology will be used? Yes.
No,
I didn't think that it was very, very deeply explained in presentation. So
no, not at all. Not at all. Really. So it will be, again, this is something that ESA takes care of, so I don't know much about it. There's a standard link in a standard frequency band. It's a higher frequency band than ESA has used previously, because actually the data rate is quite high, so you need higher frequency. And it's some band whose name I don't remember, but it's a standard downlink to the ground station, which I think is in Spain, if I'm not mistaken, it's ESAC. Don't quote me on that. And this is where then the sort of the telemetry is analyzed, the data stream, and then it's transferred then to the consortium, where we then start to process the data. In general terms, the technology exact behind this, I think, is fairly standard for ESA, but I don't know the details, I'm afraid.
Well, maybe Kate, but okay. Thank you very much. We really appreciate your presentation. I mean, really appreciate to put a little bit more light to our minds about most popular, maybe even most question of the physics today. So thank you very much.
Yeah, my pleasure.
Thank you. And this is end of the 6th TUKE Space Forum.